And so we need to talk about the assumptions of the multiple linear regression model, as usual. And they are very similar to the simple linear regression model, so I'm not going to spend a lot of time on this because they are basically the same. And the first is that we should have a linear trend between residuals and explanatory variables. So in the last chapter, we were looking at the linear trend between residuals and predicted values, but here we actually had to do it for each explanatory variable. So what we'll do is we'll create a scatter plot between the residuals and each of the explanatory variables x. The second is equivariance. So we talked that is called homoscedasticity or constant variance. So we'll use the same scatter plots as before and just try to, hopefully the variance is constant or equal across values. And we said that when this assumption is violated, we say there is heteroscedasticity. So 3, we need independent errors. So this one we can always just assume is true because ideally we should be taking a random sample. And really independent errors is a problem when we have time series or measuring things repeatedly over time, which are not the type of examples we're working on in this class. So we don't really need to worry about that one. 4 is that we have normally distributed residuals. So we can look at histograms or box plots, QQ plots for the residuals and hope that they look approximately normally distributed. And then finally, and this is the new one, so maybe I should highlight this in a different color. So the new one is that there should be no perfect linear relationship between the x variables. Another way of saying that is that the correlation between x1 and x2 is strictly less than negative, or strictly less than 1 and strictly greater than negative 1. So if we do have a perfect relationship, meaning if correlation of x1 and x2 is equal to negative 1 or equal to positive 1, then what we say is that we have something called multi-collinearity. It's another big word to impress other people, I guess. So if we have a perfect linear relationship between x1 and x2, then the model suffers from something called multi-collinearity. The problem with this is that it can essentially inflate standard errors. And so whenever you're determining whether variables are significant or not, the problem is that you're not actually determining that correctly. Your numbers are going to be off, and so you might see significance when there actually isn't any, or vice versa. So let's look at our example. So we're still working with our property value example. So this first is the scatter plot between property size and our residuals. So here we might actually say we don't have constant variance. If you kind of look at like these values, we kind of have this thing going on. So we might actually say non-constant variance or heteroscedasticity. I don't even know how to spell it. Heteroscedasticity. So that might actually be violated here. That's not the case. But is it a linear trend? I think in terms of linear trends, like, yeah, it's pretty much a straight line in terms of the trend. So I think we're good on that assumption. So I would say we're good on linear trend, probably not on equal variance there. We'll be good on independent errors because, like we said, we're always just going to take that as true. So let's look at the other variable. So between age was our other random variable, and our residuals. So this one has more constant variance. So I would say it's kind of like this. I guess there's a little bit of a trend like that, but it's nothing egregious. We're really looking for like serious problems here. And then our linear trend. Yeah, I don't know. You can kind of make it a line. Really, the problem is that if the trend looks like something like that, that's where you have a problem. So I would say we're good on this plot. And then residuals, Yeah, this is like sort of normally distributed. Again, our sample size is only 30, so it's kind of hard to tell. But I think we're okay there. So let's go ahead and say we're okay on normality of residuals. Equal variance, so this was a problem with one of our two variables. Um, but for the sake of this class, we can maybe just note it and keep moving on. There are remedies for that, but let's not, we won't concern ourselves about that right now. And then finally, let's just do a correlation between x1 and x2, which is the correlation between property size and age, and we get negative 0.1. So that's a very weak correlation, and so um, we're fine on our last assumption, which is there is no perfect linear relationship between our x variables. In fact, zero point 0.1 is very close to 0, and so that's a good thing here. So anyway, so that's how we would check all of our assumptions for this example.